Hello friends, in this video we are going to study MCQ on entropy. This MCQ will be very important for university as well as various competitive examination. Let us see the first MCQ. What is the unit of entropy? So we know that entropy is defined as change in entropy is defined as ds is equal to dq by t, where q has unit joule or kilojoule and temperatures in Kelvin. So the unit of entropy is a kilojoule per Kelvin. So first option is correct. Second questions, what is the unit of specific entropy? Now what is the difference between entropy and specific entropy? Specific entropy. Entropy is denoted by capital S and which is the ratio of Q by T. And when we call it as a specific entropy, then it is Q dot divided by T, where in earlier case this Q is in joule or kilojoule and temperature in Kelvin. Now this Q is a kilojoule per kg and divided by temperature. The unit of specific entropy is kilojoule per kg Kelvin. So this is the unit of specific entropy. Specific stands for per unit mass, and its unit is kg. So specific means per unit mass what is the change in entropy or entropy value. Okay, so specific entropy is denoted by small s, entropy is denoted by capital S. Entropy has unit joule per Kelvin or kilojoule per Kelvin. Whenever there is a specific word, then its unit is kilojoule per kg Kelvin or joule per kg Kelvin. Now in this case the unit for these questions, the answer is kilojoule per kg Kelvin. Kilojoule and joule, these are the units of heat or energy. Kilojoule per kg, it is the unit of specific energy, that may be internal energy, kinetic energy or potential energy. So these three are the units of energy, and first unit is the unit of specific entropy. Next question, cyclic integral of entropy. For example, first questions, whether entropy is a property. Yes, it is the property of a system. It is the property of a system. If you take one plane, TS plane, and where if you draw the Carnot cycle like this, 1, 2, 3, 4. These are the 4 processes, 1 to 2, 2 to 3, 3 to 4 and 4 to 1. If I want to calculate change in property of a temperature for this Carnot cycle, so I will integrate this temperature from limit 1, initial state 1 to the final state 1, because it is a cyclic integral. Cyclic integral means its initial state and final state is the same. So its integration is a t from limits 1 to 1, 1 to 1. So it becomes t1 minus t1 equal to 0. Now similarly you can calculate cyclic integral of ds from limit 1 to 1. Why 1 to 1? It is a cyclic integral. For cyclic integral, initial and final state is same. So its integration is s from limit 1 to 1. So it is a s1 minus s1 equal to 0. Here we can conclude that the cyclic integral of proper entropy is a 0, And here you can remember one thing, cyclic integral of any property is 0. Okay, you just note down cyclic integral of any property is a 0. Okay, now this property may be temperature, pressure, enthalpy, entropy, internal energy, so any property. But cyclic integral of heat transfer, that is a Q, or work transfer, that is W, is not equal to 0. So this is only true for properties. So for these questions, answer is first answer, that is 0. Cyclic integral of any property is 0. Next, entropy is now you can answer this question. Entropy, just I have told entropy is a property, and whenever it is a property, it is a state function, it is a point function. Okay, it is not a path function, it is not a path function, it is a property of a system, it is a state function, it is a point function. Okay, and it is a exact differential, exact differential. So here entropy is, it is a property, it is a point function, it is not a path function, it is a exact differential, and none of the above. All these are the wrong, so first option is correct. Next question, the entropy of an isolated system. Isolated system means there is no exchange of mass from system, and also there is no energy transfer. Okay, no mass transfer, no energy transfer. Mass and energy of these isolated systems remains constant. So the question is the entropy of an isolated system in a process. Okay, so whenever, let us consider there is a mixing process inside this inside this isolated system. For example, this is a isolated system, and you can draw, this is a partition. So here one gas is there having mass m1, this is another gas having mass m2. Remove this partition, then there is a mixing process, then there is a mixing process of gas 1 and gas 2, both are having at a different temperature, let us assume. And when partition removed, both gases are mixed with each other, and mixing process is a irreversible process. Whenever there is a irreversibility, there is a increase in entropy. Okay, now we will see the option, the entropy of an isolated system in a process. Now here any process, here I have considered mixing process, can never decrease. True, it cannot decrease. Can never increase. This may be can never increase. It may increases. So first option is wrong. It may increases. Second, can never decrease. It is a true, because entropy, this is the irreversible process, and for irreversible process entropy always increases, so it never decreases. So second option is correct. Always remains constant, wrong. Always negative, wrong. So option B is correct. Next questions, only those processes are possible in a nature for which the entropy change of the inverse is positive. Okay, so according to the principle of entropy increase, change in entropy of inverse is greater than or equal to 0. It is a greater than 0 for irreversible process and equal to 0 for reversible process. And in the inverse, whenever process it has to happen, the process must be irreversible process. And for irreversible process, change in entropy of the inverse is greater than 0. It means it is a positive. Next question, 1 kilogram of water at room temperature is brought into contact with a high temperature thermal reservoir, the entropy change of the universe is. So here change in entropy of universe is equal to change in entropy of water plus change in entropy of reservoir. Now this is here it is the heat transfer process, and during heat transfer process there is a change in entropy. And whenever there is a process is happening, means it is a possible process. And for this process the change in entropy of universe always positive. Next question. Consider the following two processes. Process A, in which a heat source at 1200 Kelvin loses 2500 kilojoule of heat to a sink at 800 Kelvin. A heat source, another uh, case in which heat source at 800 Kelvin loses 2000 kilojoule of heat to a sink at a 500 Kelvin. Which of the following statements is true? Process A1 is more irreversible than process 2. Process 2 is more irreversible than process 1. Irreversibility associated in both processes are equal. Both processes are reversible. Now here we have to calculate the change in entropy of the universe or total change in entropy in both the cases, case 1 and case 2. The process in which change in entropy is more, having more irreversibilities. That is the conclusion. If change in entropy is more is the irreversibility. So in case 1 or case 2 we should calculate the change in entropy and then we have to check it. Now first we will draw the diagram. Okay, so we will, in the first, this is a case 1 in which source which is at 1200 Kelvin loses 2500 kilojoule heat to the sink at 400 Kelvin. Now total change in entropy is a change in entropy of the source plus change in entropy of the sink. As source is rejecting heat, so it is a minus. Sink is absorbing the heat, so it is a plus. So change in entropy of the source is minus Q upon T1, and for sink plus Q upon T2. If you substitute Q and Q, T1, T2, we are getting change in entropy total or inverse is 1.041 kilojoule per Kelvin. Similarly, we can calculate for the case 2, what is the total change in entropy with the same formula. Change in entropy total is change in entropy of source plus change in entropy of the sink. Substitute the values, we are getting change in entropy is 1.5 kilojoule per Kelvin, which is a greater than case 1. So case 2 is more irreversible than the case 1. Case 2 is more irreversible than the case 1 because change in entropy in the process 2 is more as compared to process 1. So option B is correct. Process 2 is more irreversible than the process 1. Now next question. A ideal gas of mass m and temperature T1 undergoes a reversible isothermal process. So it is an isothermal process, temperature is a constant. From initial pressure P1 to the final pressure P2, the heat loss during the process is a Q. The entropy change delta S of the gas is given by. So here we can calculate this change in entropy in terms of pressure as well as volume. Okay, so as it is the isothermal process, T is equal to constant, T is equal to constant, dt is equal to differentiation of T is a dt and constant is a 0. So dt is a 0, so and du is equal to 0 because dv is equal to cv dt. As a dt is a 0, so du becomes 0. Then from the first law we can write dq is equal to du plus pdv. As a isothermal process, du is a 0, so dq is equal to pdv, and from definition of change in entropy, ds is equal to dq by t or dq is equal to tds. So that here we can substitute. So tds is equal to pdv. This formula we have derived. Now integrate it. So after integrations we are getting ds is equal to pdv divided by T. From ideal gas equation we can write PV is equal to mRT, PV equal to mRT. So P by T is equal to okay. Now P by T is equal to, from this equation we can write P by T is equal to mR by phi, mR by phi. So here we can write, instead of P by T we can write mR by phi. So fine, I will write it in next slide. Okay, here we have derived TDS is equal to PdV. TDS is equal to PdV. So ds is equal to P by phi dV, P by T dV. Just a minute, P by T dV. So according to the ideal gas equation, PV is equal to mRT. So P by T is equal to mR by phi. So this equation I can write again, ds is equal to, instead of P by T we can write mR by phi into dV. So integrate it. Now integrate it. So we are getting delta S is equal to mR ln of phi from limits 1 to 2, initial limits 1 to 2. So we are getting mR ln phi 2 minus ln phi 1. So this can be written as mR ln of phi 2 by phi 1, mR ln of phi 2 by phi 1. So this is one answer, mR ln phi 2 by phi 1. Again we can write from ideal gas equations for isothermal process. We can write what we can write. We can write, for isothermal process we can write P1 V1 is equal to P2 V2. So phi 2 by phi 1 is equal to P1 by P2. So instead of phi 2 by phi 1 we can write delta S is equal to mR ln. So this phi 2 by phi 1 we can write from above equations P1 by P2. So delta S is equal to mR ln P1 by P2 or mR ln phi 2 by phi 1. So here which option is correct? mR ln phi 2 by phi 1. So first option is correct. Okay, and if it is asked in terms of pressure, then it is mR ln P1 by P2 is the correct option. ठीक है. Next question. M1 kg of water at T1 is isobarically and adiabatically mixed with M2 kg of water at T2, but T1 is greater than T2. The entropy change of the inverse is. Okay. So this is a mixing process. Mixing process is irreversible process, and for irreversible process, change in entropy of inverse is greater than 0. So for this case, it should be necessarily positive. Okay, so first option is correct, remaining 3 are not correct. Now this is one concept required for solving next few problems or MCQs. There is one equation from the Clausius inequality. We can prove this. Okay, so from Clausius inequality directly I have taken these equations. ds is equal to dq by t. dq by t, actually this ds is greater than dq by t, and to balance this equation we need to add some term here, then this equation gets balanced, and after balancing we can write ds is equal to dq by t plus dsp. So this is the balancing parameter that can be called as entropy produced. Okay, this is the change in entropy, and this is the dq by t is a entropy transfer. Let us see, where ds is a change in entropy, and change in entropy can be positive, negative or 0. dq by t, it is an entropy flow or entropy transfer, depends upon the heat transfer q, and q can be positive, negative or 0, because for adiabatic process it is 0, positive when heat is added into the system, negative when heat is rejected by the system. dsp is called as entropy produced. It is a positive for irreversible process. Okay, it is a positive for irreversible process and 0 for reversible process. Remember this. Okay, so this dsp term is positive for irreversible and 0 for reversible process. When we take dsp 0, then we have this equation ds is equal to dq by t, and this is the definition of change in entropy, and this equation is valid for reversible process only. Therefore we have this equation ds is equal to dq by t plus dsp, where ds is change in entropy, dq by t is a entropy transfer because of heat transfer, and dsp is a entropy produced because of irreversibility. Okay, so I will write again here change in entropy. This is a change in entropy delta S is equal to heat transfer divided by temperature plus entropy generation because of irreversibility. Now let us see first question. An adiabatic process in which q is 0. Adiabatic reversible process in which S generation, entropy generation or dsp is 0. Okay, means right hand side of this equation is a 0, then delta S is equal to 0. Delta S is 0 means what? ds is a 0. Entropy is a constant, and differentiation of this is a 0. It means it is a isentropic process. For isentropic process, entropy is a constant. So here we can conclude that adiabatic reversible process is always a isentropic process. Second question, reversible isentropic process. For reversible process, dsp is a 0. For isentropic process, ds is equal to 0. Means reversible isentropic process is adiabatic process, because dq by t becomes zeros from this equation. dq by t 0, t never 0, so dq is equal to 0. It means q is equal to constant, differentiation is a 0, q is a constant means no heat transfer. So reversible isentropic process is a adiabatic process. Now third question. Adiabatic isentropic process. Adiabatic process Q is a 0. Isentropic process ds is a 0. So dsp is equal to 0 means entropy generation is 0. When it is 0, entropy generation is 0 for a reversible process. Therefore, adiabatic isentropic process is a reversible process. Now question is whether reversible process is adiabatic process. Not true. Okay, adiabatic reversible process is isentropic process. Okay, so now based on this we have next few questions we will see. Now first question, entropy change for a reversible adiabatic process is a 0. Entropy reversible process, yes, dsp is a 0. This dsp is a 0. Adiabatic process q is a 0. So this q is a 0. Then process is isentropic. True. Entropy change for a reversible adiabatic process is a 0. This is a correct. This is first statement is correct. Second, there is no heat transfer in an adiabatic process. That is also true. But R is not a correct explanation for A. Both A and R are individually true, but R is not a correct explanation of A. So option B is correct. Next, isentropic flow is irreversible and adiabatic flow, reversible and adiabatic flow, ideal fluid flow, frictionless reversible flow. For solving these questions, we should know this equation. Okay. Now, when it is a 0, when dq is a 0, dq is a 0 for adiabatic process. Second, entropy generation is a 0 for reversible process. Isentropic flow when it is a adiabatic and reversible. So in any options adiabatic and reversible, so option B in which it is a reversible adiabatic flow, it is a correct. Now next questions, choose the correct statement. The specific enthalpy and entropy of an ideal gas are the functions of temperature alone. Entropy again depends upon the heat transfer. Specific enthalpy, it depends upon temperature only. Entropy depends upon heat transfer and temperature both. So first option is not correct. Second, the specific internal energy and entropy of ideal gas are the functions of temperature. Wrong. Internal energy is a function of temperature, but entropy is not. Third, the specific enthalpy and internal energy of an ideal gas are the functions of temperature alone. That is correct because we know these equations. dH is equal to Cp dt, where Cp is a constant, and du is equal to Cv dt, where Cv is a constant. So here from these two equations we can say that specific enthalpy and internal energy of an ideal gas are the functions of temperature only. So option C is correct. So thank you for watching this video.